My name is Xiangming Zhang. I'm PhD student from City University of Hong Kong. Today I would like to introduce my latest results about low-depth quantum state preparation. So I will first begin with the background and introduce several standard quantum state preparation methods. Then we first focus on preparing a special type of quantum states called the label encoding states. And then we generalize our protocol to prepare an arbitrary quantum state. So the problem we are trying to solve is to prepare an arbitrary capital N dimensional state. And here n represents the total number of qubits we require, and I corresponds to the ith level. So for example, the basis 3 represents that we have totally 3 qubits in the states 0, 1, 1 respectively. So actually the noise robustness of the preparation depends highly on the circuit depth, and our goal is to minimize the circuit depth for state preparation. And conventionally, one may prepare a quantum state with a set of local unitary, such as the single qubit gates and CNOT gates. And these methods typically has a circuit depth and runtime of O capital N, but it requires only single and 2 qubit gates. And if the quantum random access memory is available, the preparation can be much faster, with runtime and circuit depths reduced to O log N. However, the problem is that the QRAM may require many body interactions, that a single address qubit should be able to control totally O capital N routers simultaneously, which is currently challenged. And if we have a careful look at both of the methods, we may find that only local unitaries are used. So it is natural to ask if we further allow measurements and adaptive operations, can the quantum states be prepared in a more efficient way? So our results somehow gives a positive answer to this question. And we begin with a special type of quantum states, so called label encoding states. So for vectors in this form, we encode it in a n plus 1 qubit system with a the normalization factor, and the totally n label qubits encodes the label of each element, and the value qubit, a single value qubit, encodes the values of each element, and it is represented in this form. And it can be observed that if one projects the value qubits to state 0, we directly obtain the following quantum states, corresponding to an arbitrary state of positive amplitudes. So in the following, we can just focus on this type of states, because transferring this to this is direct. And our method is inspired by these two previous works, but they are considering a different type of states, and the measurements are not considered. And suppose we have 2n qubits label encoding states, encoding VA and VB. And with these circuits, we finally project the value qubits to one of the value qubits to state plus. And if this projection is success, we can obtain a 2n dimensional label encoding states in this form. And this is actually corresponds to the direct sum of VA and VB. And this circuit has a low circuit depth that's proportional to the number of qubits. And some details are provided as follows. So after a set of control swap gates, we obtain these quantum states. And after that, we project one of the value qubits to plus states. And the key idea here is that after the projection, the last n plus 1 qubits are disentangled with the rest of the system. And the remaining systems are exactly the direct sum of VA and VB. And it should also be noted that the probability of the successful projection is always larger than 50%. So it will not be a very low value in even the worst case. And an example is given here just in case you are interested in the details. And actually, based on the transformation introduced above, we can prepare an n-dimensional label encoding states recursively in n steps, beginning with just the single or two qubit states. And each blocks here requires two input states. So one of the treatment is to prepare each of the input states sequentially. So in this way, we only need about small n blocks in this way, and we first prepare one of the inputs and then prepare another. So it can be estimated that the total runtime on average would be equals to O capital N square. And the preparation can be speed up in a parallel way in this form. So we may prepare two of the input states in parallel with multiple blocks. And moreover, we know that the preparation at each step is probabilities. So if we prepare multiple copies of the input states at the beginning, then we can have a much higher success probability and reduce the average runtime. So we estimate with numerical simulation that if we prepare only single copies of the states, the average runtime is this value. But if we prepare sufficiently large number of copies, then we can reduce the runtime to just this level. And we then discuss how to generalize this method to an arbitrary quantum state. So now our target state is as follows, and the amplitudes here can be an arbitrary complex values in case the normalization is satisfied. And we define a precise vectors v tilde here. And as this is a complex vector, we rewrite it as the summation of four positive vectors in this way. And this can always be done. And our protocol is as follows. We require four label encoding states of the positive vectors prepared in the methods introduced above, and we require two extra ancillary qubits. And with this circuit, we have four sets of control swap gates here. And after applying these gates, we project the value qubits, three of the value qubits, to the positive states, and also for the ancillary qubits. So it can be found that in this way, if all the projections success, the outputs wave functions would be in this form. And this is our target states, which can represent an arbitrary NQB states. And we also note that the average runtime is actually inversely proportional to the projection success probability, which is further proportional to the maximal absolute value of the amplitudes divided by its mean. And you can imagine that if we have a certain UIs with very large values, in this way the preparation would take extremely long time. In this way, we may perform a cutoff on the large elements, and but in this way we may sacrifice the fidelity of the preparation. And we actually found that for most of the quantum states, the fidelity is if we require the fidelity higher than threshold values, and the average runtime with respect to the accuracy actually only increase logarithmically, which is acceptable in most of the cases. And to conclude, we summarize the comparison of our protocols and existing methods with unitary or QRAMs. So all of our variants of the algorithms has a small circuit depths, but the runtime and the required ancillary qubits are varied depending on whether we prepare the states in a parallel or sequential ways. And we only need local unitaries and local measurements. And this is the advantage compared to the QRAM methods. And with this, I would like to thank you for your attention.